Have you ever driven across a bridge and noticed all those repeating triangles made of steel? Or walked into a huge sports stadium and wondered how the roof stays up without dozens of columns blocking the view? Maybe you've seen massive warehouses, airplane hangars, or train stations with giant steel frameworks stretching across enormous spaces. At first glance, these structures may look complicated. Some people even think they're just decorative patterns added by architects. But they're not. Those triangles are part of one of the most efficient structural systems ever invented, the truss structure. And once you understand how it works, you'll start seeing it everywhere. A truss is one of the simplest ideas in engineering, yet it has helped humans build longer bridges, larger buildings, and wider open spaces than ever before. The story begins with a simple problem. Imagine you're trying to cross a river. A small wooden plank might work if the river is narrow, but what happens when the river gets wider? You need a longer beam. The problem is that as a beam gets longer, it starts to bend more under its own weight. Make it long enough, and eventually it becomes too heavy, too expensive, or simply too weak. Engineers faced this challenge for centuries. They wanted structures that could span greater distances without becoming enormous solid blocks of material. The solution wasn't to use more material. The solution was to use material more intelligently. That's where the truss comes in. A truss is a framework made up of straight members connected together, usually forming a series of triangles. Instead of relying on one giant solid beam, a truss spreads the forces through many smaller members working together. Think about it like a team. One person carrying a heavy object might struggle. 10 people sharing the load can move it much more easily. A truss works the same way. Every member has a job. Every connection matters. The load gets distributed throughout the structure rather than being concentrated in one place. And that's why trusses can achieve something remarkable. They can be incredibly strong while using surprisingly little material. Now, let's talk about the basic parts of a truss. Don't worry, no complicated engineering terms are necessary. At the top, you have what's called the top chord. At the bottom, there's the bottom chord. Between them are diagonal and vertical members that connect everything together. Together, these elements create a network of triangles. That's the key feature you'll see over and over again. Triangles. Not squares. Not rectangles. Triangles. If you start paying attention to bridges and roof structures, you'll notice that engineers seem obsessed with triangles. There's a very good reason for that, which we'll explore later. But for now, just remember this. The triangle is the secret weapon of truss design. What's fascinating is that trusses aren't a modern invention. People have been using similar concepts for hundreds of years. Early wooden bridges often used truss-like arrangements. As construction technology improved, engineers began building trusses from iron and eventually steel. The Industrial Revolution accelerated this process dramatically. Suddenly, railroads needed long bridges, cities needed larger buildings, factories needed wide open floors without forests of columns. The truss became one of the most important tools in the engineer's toolbox. And it still is today. Let's look at some examples. When most people hear the word truss, they immediately think of bridges. That's understandable because some of the world's most famous bridges use truss systems. The triangular framework allows bridges to carry enormous loads while spanning long distances. Every truck, car, train, and pedestrian crossing the bridge depends on those members working together. But bridges are only the beginning. Look up the next time you're inside a large sports stadium. The roof above your head is often supported by giant steel trusses. Without them, the building would need many more columns, blocking views and reducing usable space. The same thing happens in airports. Modern airport terminals are designed to feel open and spacious. Nobody wants to walk through a terminal filled with structural columns every few meters. Trusses make those wide open spaces possible.
The same idea appears in convention centers, exhibition halls, warehouses, aircraft hangars, and industrial buildings. In fact, many of the largest indoor spaces on Earth depend on truss structures. What's even more impressive is how efficient they are. Imagine building a giant roof using a solid steel beam. It would be incredibly heavy. It would require huge amounts of material. Transportation would be difficult. Construction would be expensive. Now imagine removing most of that steel and keeping only the parts they actually need to carry forces. That's essentially what a truss does. It removes unnecessary material while maintaining strength. Engineers love efficiency, and few structural systems are as efficient as a well-designed truss. This is one reason trusses remain popular even in the age of advanced computers and modern construction techniques. The basic idea still works. In fact, some of the most sophisticated structures in the world continue to rely on principles that engineers have understood for generations. Another reason trusses are so common is flexibility. They can be small or enormous. They can be made from wood, steel, aluminum, or other materials. They can support roofs, bridges, towers, and many other structures. The same fundamental concept adapts to countless different situations. That's a sign of truly great engineering. Simple enough to understand, powerful enough to solve major problems. If you've ever built something with construction toys as a child, you've probably discovered this idea yourself. When you connect pieces into triangular shapes, the structure suddenly feels stronger. It wobbles less. It holds its shape better. The same principle applies whether you're building a toy model or a bridge that carries thousands of vehicles every day. So the next time you see a bridge covered in steel triangles or a giant stadium roof stretching across an enormous space, you'll know there's more going on than meets the eye. What looks like a collection of simple shapes is actually the result of centuries of engineering knowledge. A truss isn't just a bunch of steel bars connected together. It's a carefully organized system designed to move forces efficiently, minimize material usage, and create structures that would otherwise be impossible. And there's one question that naturally follows. Why triangles? Why do engineers trust this shape so much? Why not squares, rectangles, or other geometric patterns? The answer lies in one of the most important principles in structural engineering, and it explains why the triangle became the foundation of truss design across the world.
Okay, just now we talked about what a truss structure is and why engineers use it in bridges, stadiums, airports, and warehouses. But we left one big question unanswered. Why triangles? Seriously, have you ever noticed how obsessed engineers seem to be with triangles? Look at a steel bridge. Triangles. Look at a transmission tower. Triangles. Look at a roof truss. More triangles. It's almost as if engineers discovered one shape they liked and decided to use it everywhere. Of course, that's not what happened. The reason triangles appear everywhere in structural engineering is because they possess a unique characteristic that other common shapes simply don't have. They are naturally stable. To understand why, let's do a simple thought experiment. Imagine you build a square using 4 sticks connected at the corners. At first glance, it seems solid. It looks like a proper shape. But now imagine pushing gently on one side. What happens? The square changes shape. It becomes a diamond. Push a little more and it deforms even further. The lengths of the sticks haven't changed. The connections are still intact. Yet the shape itself has become distorted. That's a problem. Now let's try the same thing with a triangle. Take 3 sticks and connect them at the corners. Push on one side. What happens? Almost nothing. The shape resists deformation. For the triangle to change shape, at least one of its sides would have to change length. And that's much harder to do. This simple difference is one of the most important discoveries in structural engineering. Squares can deform. Rectangles can deform. Triangles resist deformation. That's why engineers love them. Nature seems to appreciate this principle too. If you look closely, you'll find triangular patterns all around you. Mountain bike frames often use triangular arrangements. Construction cranes rely heavily on triangular geometry. Even the human body uses triangular relationships between bones and muscles to create stability and movement.
The triangle isn't just an engineering trick. It's one of the most efficient ways to create a stable structure. Now imagine you're designing a bridge. The bridge must carry thousands of vehicles every day. Strong winds might push against it. Temperature changes might cause expansion and contraction. The structure needs to stay stable under all these conditions. Would you rather trust a shape that can easily deform, or one that naturally holds its form? The choice becomes obvious. That's why engineers take larger shapes and divide them into smaller triangles. A bridge may look incredibly complex from a distance, but if you zoom in, you'll often discover that it's really just a collection of interconnected triangles working together. The same thing happens in roof structures. Suppose you're designing a stadium roof that spans over a football field. The roof must support its own weight. It must resist wind loads. In some places, it must even support heavy snow. A simple rectangular framework would struggle. A triangular framework performs much better. This brings us to another important idea. Most people think structures stay up because the materials are extremely strong. That's only partly true. Good engineering isn't just about strength. It's about geometry. A clever shape can often outperform a stronger material used inefficiently. Think about an empty soda can. If you stand on an upright soda can carefully, it can support surprisingly large loads. But if you crush the side slightly, it suddenly collapses. The material didn't change. The geometry changed. And geometry matters. Truss structures are a perfect example of this principle. They achieve impressive strength not simply because they use steel, but because they use geometry intelligently. The triangular arrangement allows forces to travel efficiently through the structure. This leads to another common misunderstanding. Many people imagine that every part of a bridge or roof bends under load. In reality, truss members are designed to do something different. Instead of bending, most members primarily experience either tension or compression. Let's break that down. Imagine pulling on a rope. The rope experiences tension. The force is trying to stretch it. Now imagine pushing down on a drinking straw. The straw experiences compression. The force is trying to squeeze it. Those are two very different types of forces. One pulls, one pushes. A truss transforms complex loads into a combination of these simpler forces. Some members get pulled, some members get pushed. Together, they support the entire structure. This is one reason trusses are so efficient. Steel performs exceptionally well when carrying tension. It also performs well under compression when designed properly. Rather than forcing large beams to bend, engineers allow truss members to specialize. Each member performs a specific job. Some resist pulling, others resist pushing. The workload gets distributed throughout the structure. You can think of it like a sports team. A football team doesn't ask every player to do everything. Different players have different roles. The team succeeds because everyone contributes. A truss works the same way. Each member handles a portion of the load. No single member carries the entire burden. As a result, the structure becomes both stronger and more efficient. This principle explains why trusses can span such enormous distances. A traditional solid beam becomes heavier and less efficient as it gets longer. Eventually, its own weight becomes a major problem. A truss avoids much of this issue. By organizing material into a triangular framework, engineers can achieve impressive spans without excessive weight. That's why you'll find trusses in places where long spans are essential. Bridges crossing rivers, airport terminals, sports arenas, concert halls, aircraft hangars, industrial warehouses. These structures need large open spaces. People don't want rows of columns blocking movement or visibility. Trusses help solve that challenge. In fact, some modern roof trusses can span hundreds of feet while supporting enormous loads. And all of that performance begins with a simple geometric idea. The triangle. It's not flashy. It's not complicated. You can draw one in seconds. Yet that simple shape changed the history of engineering. It allowed builders to create larger structures, longer bridges, and wider open spaces than previous generations could imagine. The next time you see a truss bridge or a stadium roof, try looking beyond the steel itself. Focus on the pattern. Look at the repeating triangles. Those triangles are doing far more than creating an interesting appearance. They are the reason the entire structure remains stable. They are the reason forces can travel safely through the system. And they are the reason trusses became one of the most efficient structural solutions ever developed. Of course, knowing why triangles are stable is only part of the story. A bigger question remains. When a truck drives across a bridge, how does the weight actually move through all those members? Which parts are being pulled? Which parts are being pushed? And how does the load eventually reach the ground? That's where the real mechanics of a truss begin. And it's one of the most fascinating aspects of structural engineering.
By now, we know two important things. First, a truss is made up of many connected members arranged into triangles. Second, triangles are incredibly stable, which is why engineers use them everywhere. But here's the question that separates seeing a truss from understanding a truss. When a load is placed on a truss, what actually happens? Imagine a truck driving across a bridge, or thousands of fans sitting beneath a stadium roof, or heavy equipment hanging from a warehouse structure. Where does all that weight go? Does one member carry everything? Do all the members carry the same amount? How does the force eventually reach the ground? The answer is one of the most fascinating ideas in structural engineering. A truss doesn't fight a load in one place. It spreads the load throughout the entire structure. Let's start with a simple example. Imagine a person standing on the middle of a truss bridge. That person's weight creates a downward force. Gravity is constantly pulling them toward the earth. The bridge must resist that force. If the bridge fails to do so, the person falls. Simple enough. But the bridge doesn't magically know what to do. The force must travel somewhere. Think of it like water flowing through a network of pipes. When weight is applied to a truss, the force begins moving through the members. It travels from connection to connection, member to member, until it eventually reaches the supports and then the ground. Engineers often call this a load path. In simple terms, a load path is the route that force follows through a structure. Every successful structure has a clear load path. If the load path is interrupted, problems begin. Let's break down the journey. A load is applied. The force enters the truss. The members react. The force moves through the framework. The supports receive the load. The foundation transfers it into the soil. That's the entire story. Everything engineers design revolves around making that journey safe and efficient. Now here's where things get interesting. Not every member reacts in the same way. Some members get stretched, others get squeezed. Remember the concepts from the previous part? Tension and compression. These two forces are the language of trusses. Imagine the game of tug of war. The rope is being pulled. That's tension. Now imagine squeezing a spring between your hands. That's compression. A truss contains both. At any given moment, some members are being pulled while others are being pushed. Together, they balance the load. This is why a truss can be so efficient. Instead of forcing large beams to bend, engineers arrange members so they primarily experience tension or compression. Materials generally perform better this way. And when materials work more efficiently, less material is required. That means lower cost, lower weight, and often better performance. Let's visualize this with a simple roof truss. Imagine a large roof covering a sports arena. The roof's weight pushes downward. The top portion of the truss is usually compressed. The bottom portion is often stretched. Meanwhile, the diagonal members help transfer forces between different parts of the structure. Every member contributes. Every member has a job. Remove the wrong member and the entire system changes. That's one reason engineers take truss design so seriously. A truss isn't just a collection of random steel bars. It's a carefully balanced network. Every piece depends on the others. You can think of it like a chain. Every link matters. If one critical link breaks, the entire system becomes vulnerable. History has provided some painful lessons about this.
There have been famous bridge failures where a single member failure triggered a chain reaction throughout the structure. One problem led to another, then another, until the entire structure collapsed. That's why modern engineers spent enormous amounts of time analyzing forces and checking safety margins. Today, powerful computer software can simulate thousands of loading conditions before construction even begins. But the fundamental principles remain the same. Loads move through members. Members resist forces. Supports transfer loads to the ground. Now let's talk about something many people notice when looking at truss bridges. Not all trusses look the same. Some have vertical members. Some don't. Some use long diagonals. Others use shorter ones. Some look simple. Others look incredibly complex. Why? Because engineers have developed different truss arrangements for different situations. Over time, several famous truss configurations became widely used. One of the most common is the Pratt truss. The Pratt truss became extremely popular for bridges because its diagonal members work efficiently under typical loading conditions. For decades, it was one of the most successful bridge designs in the world. Another famous example is the Howe truss. At first glance, it looks similar to a Pratt truss, but the diagonals point in the opposite direction. That seemingly small difference changes how forces flow through the structure. Then there's the Warren truss. If you've ever seen a bridge made almost entirely of repeating triangles, there's a good chance it was a Warren truss. Its clean, simple geometry distributes loads efficiently while using relatively few members. Each of these designs follows the same basic principle: move loads safely and efficiently. The differences come from how engineers choose to arrange the members. It's a bit like designing different road networks. All roads move vehicles from one place to another, but some layouts are better for certain conditions than others. The same is true for trusses. Different arrangements create different force paths. Different force paths create different structural behavior. This is where structural engineering becomes both science and art. The science tells engineers how forces behave. The art lies in choosing the best arrangement for a particular project. A bridge crossing a river may need one solution. A stadium roof may need another. An aircraft hangar may require something completely different. Yet all of them rely on the same fundamental idea: control the path of forces, guide loads safely through the structure, deliver those loads to the ground. When you look at a truss through this lens, it becomes much more than a pattern of triangles. It becomes a force management system. Every member is part of a larger strategy. Every connection plays a role. Every load follows a path. And once you understand that concept, you'll never see a bridge the same way again. You'll start noticing how the forces are likely moving. You'll wonder which members are in tension, which members are in compression, which pieces are carrying the heaviest loads. That's when you begin thinking like an engineer. And as engineers continued refining truss systems over the centuries, they created several distinct truss types that became famous around the world. Some were optimized for bridges, some for timber construction, some for steel structures. Each one solved problems in a slightly different way, and those designs shaped some of the most important infrastructure ever built.
By now, we've learned what a truss is, why triangles are so important, and how loads travel through a truss structure. But if you've ever looked at different bridges, you may have noticed something interesting. Not all trusses look the same. Some have vertical members, some don't. Some are filled with diagonal bars pointing one direction, others seem to zigzag back and forth. At first glance, they can look completely different, yet they're all trusses. So why did engineers create so many different designs? The answer is simple. Different projects have different requirements. A bridge carrying trains faces different challenges than a warehouse roof. A wooden structure behaves differently from a steel structure. A design that works perfectly in one situation might not be the best choice in another. Over hundreds of years, engineers experimented with different arrangements of members, eventually creating several famous truss types that are still used and studied today. Let's look at the most important ones. The Pratt truss. If there were a hall of fame for truss designs, the Pratt truss would definitely be in it. First patented in the United States in the mid-1800s, it quickly became one of the most widely used bridge designs in the world. The Pratt truss is easy to recognize. Its diagonal members generally slope toward the center of the span.
The vertical members connect the top and bottom chords. The design looks clean, organized, and highly symmetrical. But the real beauty isn't how it looks, it's how it works. Under typical bridge loading conditions, the diagonal members are primarily in tension, meaning they're being pulled. The vertical members are usually in compression, meaning they're being pushed. This arrangement works particularly well with steel because steel performs exceptionally well under tension. As railroads expanded across North America and other parts of the world, Pratt trusses became extremely popular. Thousands of bridges were built using this configuration. Many are still standing today. That's always a good sign in engineering. When a design survives for more than a century, it probably did something right. The Howe truss. At first glance, the Howe truss looks surprisingly similar to the Pratt truss, but there's one important difference. The diagonals point in the opposite direction. That small change completely alters how the forces move through the structure. In a Howe truss, the diagonal members are usually in compression, while the vertical members often carry tension. This made the design especially useful when timber was commonly used for large structures. Wood generally performs better in compression than in tension. As a result, the Howe truss became a popular choice for early wooden bridges. During the 19th century, countless railroad bridges used this system. If you travel through areas with preserved historic bridges, there's a good chance you'll encounter a Howe truss. It represents an important chapter in the evolution of structural engineering. What's fascinating is how such a small geometric change can completely alter structural behavior. To a casual observer, Pratt and Howe trusses may look almost identical. To an engineer, they're very different machines. The Warren truss. Now let's talk about one of the simplest and most elegant truss designs ever created, the Warren truss. Unlike the Pratt and Howe trusses, the Warren truss often uses a continuous pattern of repeating triangles. No complicated arrangement, no crowded framework, just a clean zigzag pattern stretching across the span. The simplicity is part of its appeal. Because it uses fewer members, construction can be faster and more economical. The load tends to distribute relatively evenly throughout the structure, making the design efficient for many applications. This type of truss became popular for both bridges and roof systems. Even today, you'll find Warren trusses in industrial buildings, warehouses, pedestrian bridges, and various steel structures. Many engineers appreciate the Warren truss because it demonstrates an important engineering principle. Sometimes the simplest solution is also the smartest. The design doesn't rely on complexity. It relies on geometry. And geometry, when used correctly, can accomplish remarkable things. The K-truss. As structures became larger and spans increased, engineers began searching for ways to improve stability even further. This led to the development of the K-truss. When viewed from the side, portions of the framework resemble the letter K, hence the name. The purpose of this design is to shorten the length of certain compression members. Why does that matter? Because long compression members can buckle. Think about trying to compress a long, thin stick. Instead of crushing directly, it often bends sideways. That's buckling, and buckling is one of the biggest concerns in structural engineering. By dividing members into shorter segments, the K-truss helps reduce this risk. The result is a stronger and more stable structure, especially for longer spans and heavier loads. Although K-trusses can be more complicated to fabricate and construct, they provide important advantages in specific situations. That's often the trade-off in engineering. Greater performance sometimes comes with greater complexity. Other truss types. Of course, these aren't the only truss designs ever created. Engineers have developed dozens of variations over the years. Some examples include Baltimore truss, Parker truss, camelback truss, Fink truss, bowstring truss, Pennsylvania truss. Each one was created to solve a particular challenge. Some reduce material usage, some improve stability, some work better for long spans, others simplify construction. What all of them share is the same fundamental principle. They use triangular geometry to control forces efficiently. No matter how different they appear, they all belong to the same structural family. Why so many designs? People often ask why engineers didn't simply choose one truss type and use it everywhere. The reason is that structural engineering is all about optimization. Imagine buying a vehicle. If you need to haul heavy equipment, you might choose a truck. If you want fuel efficiency, you might choose a compact car. If you need to transport dozens of passengers, you might choose a bus. None of these vehicles is universally best. They're optimized for different tasks. Trusses are exactly the same. A bridge carrying freight trains may need one solution. A stadium roof may need another. A warehouse may require something different altogether. The goal isn't to find the perfect truss. The goal is to find the right truss for the job. That's what engineers do every day. When you look at a truss bridge now, you're seeing much more than a collection of steel members. You're looking at a design that may have been refined over generations. Every diagonal, every vertical, every connection exists for a reason. The arrangement wasn't chosen randomly. It was chosen because it helps control forces in the most effective way possible. And while these classic truss designs transformed bridge engineering, their influence didn't stop there. As cities grew larger and buildings became more ambitious, engineers began using trusses in entirely new ways. Soon, trusses weren't just supporting bridges. They were helping create some of the largest indoor spaces ever built. Massive stadiums, airport terminals, exhibition halls, and industrial facilities that would have been impossible without them.
When most people hear the word truss, they immediately think of bridges. That's understandable. Some of the most famous bridges in the world use truss systems, and they're often the first example shown in engineering textbooks. But here's something surprising. Some of the most impressive uses of trusses aren't found on bridges at all. They're found above our heads. In stadiums, in airports, in exhibition centers, in factories, in aircraft hangars, in some of the largest buildings ever constructed. In fact, if trusses had never been invented, modern architecture would look very different. Many of the huge open spaces we take for granted today simply wouldn't exist. To understand why, let's imagine a problem. Suppose you're an architect designing a sports stadium. You need to cover tens of thousands of seats with a roof. Fans want protection from rain and sun. The owner wants the building to look impressive. But there's one major challenge. Nobody wants columns blocking the view. Imagine paying for a seat at a championship game only to spend the entire match staring at a giant concrete column. Not exactly ideal. So the roof must span an enormous distance without intermediate supports. That's where trusses become incredibly valuable. Instead of using massive solid beams, engineers create giant truss systems that can stretch across huge distances while remaining relatively lightweight. The result is a clear, open space beneath the roof. Everyone gets an unobstructed view, and the structure remains safe and efficient. This is one reason why modern stadiums rely heavily on truss systems. Some stadium roofs span well over 100 meters. Without trusses, such designs would be far more difficult and expensive to achieve. The same principle applies to airports. Think about the last time you walked through a major airport terminal. Most modern terminals feel open and spacious. Passengers move freely. Natural light enters through large glass walls. There are wide waiting areas and long sidelines. Now imagine replacing that open space with rows and rows of structural columns. The terminal would feel crowded and confusing. Movement would become more difficult. The entire experience would change. Trusses allow architects to create these vast column-free spaces. By transferring loads efficiently across long distances, they make modern airport design possible. Every time you walk through a large terminal, you're benefiting from structural engineering that most travelers never notice. The roof quietly does its job while thousands of people pass underneath. Exhibition centers provide another great example. These buildings often host trade shows, conventions, concerts, and large public events. One week, the space might contain hundreds of exhibition booths. The next week, it could be transformed into a concert venue. Flexibility is essential. Columns would limit that flexibility. Open space is valuable. Trusses help create that open space. Many exhibition halls use enormous roof trusses that span across the entire building. From the floor, visitors may barely notice them, but those steel frameworks are carrying thousands of tons of load above their heads. The larger the building becomes, the more important the truss system often becomes. Industrial buildings tell a similar story. Warehouses and factories need wide, unobstructed floor areas. Forklifts must move freely. Machinery must be positioned efficiently. Storage systems require flexibility. Columns can interfere with operations. For that reason, steel roof trusses became one of the defining features of industrial construction. Walk into a large warehouse and look up. You'll probably see long steel trusses stretching from one side of the building to the other. They're doing exactly what engineers designed them to do, creating maximum usable space with minimum material. This idea becomes even more important in aircraft hangars. Airplanes are huge. A hangar must provide enough space for aircraft to enter, exit, and undergo maintenance. Large columns inside the structure would create major obstacles. Engineers solved this problem using long-span truss systems. Some hangars contain trusses so large that they look almost like bridges suspended above the floor. And in a way, that's exactly what they are. Instead of carrying vehicles across water, they're carrying roof loads across open space. What's remarkable is how efficient trusses are at this task. Imagine trying to cover a stadium using a giant solid steel beam. The beam would be incredibly heavy. Transporting it would be difficult. Lifting it into place would require enormous equipment. The cost would be enormous.
A truss achieves similar structural performance while using far less material. By arranging members into triangular patterns, engineers remove much of the unnecessary weight. Only the material needed to carry forces remains. This is one reason trusses are considered such an elegant engineering solution. They do more with less. That's a principle engineers love. And as technology advanced, truss systems became even more sophisticated. Early trusses were often built from timber. Later, iron became common. Then steel transformed the possibilities. Today, engineers can use advanced computer modeling to design trusses with incredible precision. Software can analyze thousands of loading conditions: wind loads, snow loads, seismic forces, thermal expansion, maintenance loads. Engineers can simulate years of structural behavior before construction even begins. Yet despite all this advanced technology, the fundamental idea remains the same: triangles, load paths, tension, compression. The core principles haven't changed. The tools have improved, but the physics is still the same. Some of the world's most iconic buildings demonstrate this beautifully. Look closely at modern stadium roofs, observe large airport terminals, examine major exhibition halls. You'll often discover enormous truss systems hidden within the architecture. Sometimes they're exposed and celebrated as part of the building's appearance. Sometimes they're concealed behind ceilings and architectural finishes. Either way, they're doing the heavy lifting, literally. One of the most fascinating aspects of structural engineering is that the strongest structures are often the ones people barely notice. Visitors admire the architecture. They enjoy the open spaces. They appreciate the views. Rarely do they stop and think about the structural system making it all possible. Yet without those trusses, the experience would be completely different. The next time you're inside a stadium, airport, convention center, or warehouse, take a moment to look up. You might see a network of steel members forming familiar triangular patterns. Those triangles are creating the space around you. They're allowing architects to dream bigger. They're allowing engineers to span greater distances. And they're quietly supporting some of the largest buildings humanity has ever constructed. Of course, no structural system is perfect. Trusses offer enormous advantages, but they also come with challenges. They save material, but they require careful design. They create large open spaces, but they can be complex to build and maintain. Like every engineering solution, they involve trade-offs. And understanding those trade-offs is the key to understanding why engineers choose trusses and when they choose something else instead.
Over the course of this series, we've explored what truss structures are, why triangles are so important, how forces move through a truss, the major types of trusses, and how they help create some of the largest buildings and bridges in the world. At this point, one question remains. If trusses are so effective, why isn't everything built with trusses? Why do some buildings use concrete frames? Why do others use shear walls or different structural systems? The answer is simple. No structural system is perfect. Every engineering solution comes with strengths and weaknesses. The job of an engineer is not to find a perfect system. It's to find the most suitable system for a specific project. Let's start with what makes trusses so powerful. Advantage number 1, outstanding strength-to-weight ratio. One of the biggest reasons engineers love trusses is efficiency. A truss can carry enormous loads while using relatively little material. Think about the difference between a solid steel beam and a truss. A solid beam contains material throughout its entire volume. A truss removes much of that material and keeps only what is necessary to transfer forces. The result is a structure that can achieve impressive strength without excessive weight. In engineering, lighter often means better. Lighter structures require smaller foundations. They are easier to transport. They are often faster to assemble. And they usually cost less. This ability to do more with less is one of the defining characteristics of good engineering. Trusses are a perfect example of that philosophy. Advantage number 2, long spans and open spaces. This is perhaps the most visible advantage. Trusses can span large distances without intermediate supports. That means fewer columns. Fewer columns mean more usable space. Imagine a football stadium filled with structural columns every few meters. The experience would be terrible. Imagine an airport terminal where passengers constantly navigate around support columns. The space would feel crowded and inefficient. Trusses solve this problem by carrying loads across long distances. That's why they are so common in stadiums, airports, exhibition halls, aircraft hangars, factories, warehouses, large bridges. Whenever engineers need a large open area, trusses often become one of the first solutions considered. Advantage number 3, material savings. Steel is expensive. Concrete is expensive. Construction in general is expensive. Because trusses use material efficiently, they can reduce overall material consumption. Less material often means lower project costs.
It can also reduce environmental impact. Modern construction increasingly focuses on sustainability. Using fewer resources while maintaining performance is becoming more important every year. Trusses align well with that goal. By placing material only where it is needed, they minimize waste. Advantage number 4. Prefabrication and faster construction. Many truss systems can be manufactured in factories before arriving at the construction site. This process is called prefabrication. Instead of building everything on-site, large sections can be assembled in a controlled environment and then transported for installation. This offers several benefits: better quality control, faster construction, reduced labor costs, improved safety. Modern construction increasingly relies on prefabricated components, and trusses fit naturally into that approach. But trusses also have disadvantages. Every engineering solution involves trade-offs. The same features that make trusses powerful can also create challenges. Disadvantage number 1. Complex connections. When people look at a truss, they often focus on the members. Engineers often focus on the connections. Why? Because connections are critical. Every force moving through a truss eventually passes through joints and connection points. Designing these connections can be surprisingly complicated. Bolts, welds, plates, gusset connections. Each must be carefully designed and inspected. In many projects, connection design becomes one of the most challenging parts of the entire structure. Disadvantage number 2. Maintenance requirements. A truss may contain dozens, hundreds, or even thousands of individual members. Each member must remain in good condition. Steel structures require protection from corrosion. Connections require inspection. Damaged components may need replacement. This is especially important for bridges exposed to weather year-round. Over time, maintenance becomes a major part of the structure's life cycle. A truss that is ignored for decades can develop serious problems. A truss that is properly maintained can remain functional for generations. Disadvantage number 3. Greater design complexity. A simple concrete wall may be relatively straightforward. A large truss system is often much more complicated. Engineers must analyze wind loads, snow loads, seismic forces, dynamic loads, buckling risks, fatigue behavior, connection performance. Modern software helps enormously, but complexity still exists. The larger the span becomes, the more important detailed analysis becomes. There is very little room for error when designing a structure that may support thousands of people. Disadvantage number 4. Space requirements. Although trusses save material, they often require depth. A truss usually needs a certain height to work efficiently. This means roof systems can become relatively deep. Architects and engineers must coordinate carefully. Sometimes a project simply doesn't have enough space to accommodate a large truss. In those situations, alternative structural systems may be more practical. The future of truss structures. Some people assume trusses are old technology. After all, many famous truss bridges were built over a century ago. But that assumption couldn't be more wrong. Trusses continue to evolve. In many ways, they're becoming more important than ever. Today's engineers use advanced software to optimize truss designs with incredible precision. Computers can evaluate thousands of possible configurations and identify highly efficient solutions. Materials are improving as well. High-strength steel allows longer spans and lighter structures. Advanced fabrication methods improve accuracy and quality. Digital construction technologies reduce errors during assembly. One exciting development is the growing use of space trusses. Unlike traditional flat trusses, space trusses extend in 3 dimensions. They create lightweight yet extremely rigid structural systems capable of covering enormous areas. Many modern airports and exhibition centers use these systems. Another major trend is the rise of building information modeling, often called BIM. BIM allows architects, engineers, contractors, and owners to collaborate using digital models. Complex truss systems can now be designed, analyzed, fabricated, and installed with a level of coordination that previous generations could only dream about. Automation and robotics are also beginning to influence construction. In the future, portions of large truss systems may be manufactured with even greater precision and efficiency than today. Final thoughts. The next time you walk through an airport terminal, sit beneath a stadium roof, enter a giant warehouse, or drive across a bridge, take a moment to look around. Chances are, a truss structure is helping support the space you're using. What appears to be a simple arrangement of triangles is actually one of the most successful engineering ideas ever developed. It's elegant. It's efficient. It's remarkably powerful. For centuries, trusses have allowed humanity to build farther, wider, and higher. They transformed transportation. They changed architecture. They created spaces that once seemed impossible. And despite all the technological advances of a modern world, their core principle remains beautifully simple. A collection of triangles, working together, carrying forces, creating possibilities. That's the genius of the truss structure. And it's a perfect reminder that sometimes the most powerful engineering solutions are also the simplest.